a talk from Michael Reif, Florian Kübler, Dominik Helm, Bernd Herrmann, Michael Eichberg, and Mira Mezzini from TU Darmstadt. And I will let them speak for themselves.
Hello everyone, my name is Michael Reif from the Technical University of Darmstadt, and now I'll present our work about our new abstract interpretation-based intermediate representation. So, what is the problem we are trying to solve? We want to implement static analysis, and doing so directly on bytecode is quite troublesome. That is, because bytecode has a lot of different instructions actually doing a similar thing, and one also has to take care about Java Bytecode's operand stack and its implicit control flow. That's also the reason why most static analysis frameworks for Java usually first transform Java Bytecode in an intermediate representation before actually analyzing it. And the problem we have is that OPAL still directly works on Java Bytecode and so do all its static analyses, which makes it pretty hard to use, especially for beginners, because it requires a lot of knowledge about Java Bytecode. To facilitate the development of static analyses, we wanted OPAL also benefits from having an intermediate representation, especially benefiting from a limited instruction set. For example, loading a constant integer in Java Bytecode has 4 different instructions, whereas we could only use one for it, right? But intermediate representation also had other benefits, such as explicit control flow, that all the intermediate values have explicit names, and additionally also the nested control flow and the complex impressions are simplified. So most intermediate representations are based on a 3 address code, in short TAC, or additionally use the static single assignment form, in short SSA. Just to get us all on the same page, let's refresh what TAC and SSA actually is. First, to 3 address code. Here, every statement has at most 3 operands, 2 for their operators and 1 to store the result. It can also have less statements with less operators. Usually, all different statements types are still available, such as conditional and unconditional jumps, method calls and returns, and it can also have some custom instructions. To demonstrate its effect, let's consider the example in the bottom left corner. It shows a rather complex expression with 4 operands. When we transform these expressions to TAC, it will be simplified into 2 different statements with 3 operators. SSA refers more to a property of a representation. As the name suggests, each variable is assigned exactly once. That means that it's always known where variable that it's used is defined. To keep that property when branches are present, SSA forms usually provide fee nodes to select the value from a certain branch. As we can see below, this property immediately facilitates optimizations. When we rewrite the code from the left to SSA form, we see that y1 is never used and therefore could be removed. And because we don't want to reinvent the wheel, we wanted to check what all the other frameworks like Soot, Vala, or Doop are actually doing. All of them use intermediate representations, which are typed. Soot, for example, uses Jimple, which is an optimized TAC representation that already applied some optimizations, for example, constant propagation. Doop, in contrast, uses Soot's Jimple representation, which is basically Jimple transformed to SSA. And Vala has his own representation, which is also in an extended SSA form, and additionally captures local path conditions, which describe how to get in a branch. And all those representations are differently typed to a different precision. So when we consider the following example on the left-hand side of the slide, we see in line 1 that there's a collection, and then depending on some condition, in one branch, the collection is either instantiated to an array list or to a vector. And then in line 7, we have a call in that collection and add null. What Vala's IR is capturing here is only the declared type of a collection. So in line 7, when we would consider a class hierarchy analysis call graph, Vala would consider all subtypes of collection as viable targets. Soot does a bit more of optimizations here, as it computes the upper type bound of C from both branches, which basically looks for a common supertype of array list and vector, which in that case is list. So in a class array case, only all subtypes of list would be considered there. But optimally, we would like to have the information available that C can either be an array list or a vector, because that's the only types that are assigned to C. With that in mind, we finally come to our approach. Since I already said in the beginning that we use OPAL, OPAL's unique feature is that it does interprocedural abstract interpretations of a method's bytecode, and when we could use the information gained from the AI, that would allow us to build different intermediate representations at different precision levels. Because when we exchange and customize the underlying abstract domains that are used by AI, then we can also adapt the outcoming intermediate presentations, because we probably have more information. OPAL usually already computes the method's control flow graph and also the views and use that information during AI and use it there. So when we have more abstract domains and detect that path and so on, then it would also result in simpler and less AR code. OPAL's abstract interpretation is easily configured via Scala's mix and composition. So the semantics for each set of closely related instructions and bytecode is implemented in a single trait. So for example, there's a trait for integer-based operations where you can specify how certain integer instructions should be interpreted. And there are also domains for reference value-based operations and so on. For example, like instance objects, casts, tests against null, and other things. And those different traits can be stacked, and they can also interact together over a shared set of query methods. For example, when you have a trait that handles reference values, they have to implement the method is null, and then this is, for example, required for method invocations. Because when you know that a value can be null or can't be null, then you either don't have to or you explicitly have to trigger a null pointer exception in Java. But I don't want to go into too much detail here, so when you want to know how OPAL's AI works, you can follow the link or look into the Soot paper from 2014 and get more details there. All you have to know here is basically that TACAI uses pre-configured domains from OPAL, which are just named like level 0, level 1, and level 2. Our intermediate representation called TACAI has several features. At first, and it's an IR, which is in straight dress code, and it is also an SSR-like form. It's only SSR-like, I will come to that in a second. As I just said, you can configure it by using different abstract domains which influence the AI construction. Currently, we have 3 representations available from the 3 abstract domains that are pre-configured in OPAL. We have a TACAI L0, L1, and L2, and those explicitly encode the views information and use def information. They are just available in the IR and you can access them. It's only SSR-like because TACAI doesn't support phi nodes. Instead, it uses union and intersection types for referent types values, and for primitives values they are captured via abstract sets, ranges, or values. But that the actual representation depends on the AI abstract interpretation domains that are used and how the values are abstractly interpreted. And the AI allows you to also encode additional information, for example, if a variable is null or not. So before we jump into how TACAI actually looks, we want to consider the following source code example. At the first 2 lines, there are just 2 method definitions. They're pretty simple. One just throws the runtime exceptions and the other one just prints a string. And then there's the method we will see TACAI in the next slides for. There's a method m, which has 1 parameter here. It is serializable, called serializable. In the first line of a method, we check if the given parameter is null, and if it's null, we return. We already gained some information here. Then we have an object O, a local variable O, which casts is serializable to a clonable, and then we also call the object's toString method. save the string s, and then we create one new string buffer, sb0, and append s using the sb0's append method, and get another string buffer. For all of those that don't know the string buffer interface, the string buffer usually returns a self-reference. And then we have an if check if those are basically the same reference or not. And if not, we throw a runtime exception. That should basically never be the case, right? But we can't know from that code or from the bytecode. And then we call the p method to print a string, and we print a string that from the actual string buffer. Okay, how does the TAC from this look like? So the baseline TAC, which is the least precise TAC representation, is roughly as precise as Jimple, and this does not provide much more information than the original bytecode. But on the left side we see how it looks like. We still have the if statement, and if it's p1, so p1 is the parameter we get here, is not null, then we jump to the next statement, otherwise we return. Then we have the class to clonable, and afterwards we have the information that p1 is the subtype of clonable. Then we continue basically like the bytecode. It's nothing interesting. It basically resembles what we just saw in source code. One interesting thing here is that what I just said is that TACAI also catches their views chains immediately. So what you see at the sample at the right hand side is basically immediately available in TAC. It says for the parameters the use sites at A and 11. P0 resembles this parameter of the method, and P1 resembles the parameter that is passed to the method, which basically says the origin. When we use the domain L1 to generate the TAC, we have already a bit more information, and all the changes are marked in blue color. TACAI L1 already computes union and intersection types, and we can see that at line 2. Previously, from TAC L0, we knew that P1 is a subtype of clonable, but now we know because it originally was serializable, so the parameter 1 has to be serializable, and then it was casted to clonable. We know that's an intersection type from serializable with clonable. And we also know that P1 is not null because of the null check from line 0. Other things that TACAI L1 already provides are must alias information for reference types, and it also applies constant folding and propagation to integer values, which can't be seen here. And also it prunes that paths if it's possible. So when we know that a condition is always true or false, then it already removes the code. This considered, we can jump forward to the next step, which is the most precise version of TACAI, the level 2 domain. And here again all the differences are marked in blue. And here we interestingly see that the result from the second string builder is ignored. And that's why the rest of it is removed, because it has no use. Please note that at line 7 we now introduce a no-op. That's because the CFG is usually not rewritten, and the basic block can't be empty, so that's why we have to add a no-op here. And now the if check and the call to the method that throws the runtime exception could be removed, because we know that the variable is never used and the expression value is ignored. And that's possible because TAC L2 does selective method inlining, which is particularly useful for fluent interfaces, such as the string builder string buffer is 1 with append. Fluent interfaces have the property that they're usually allowed to chain method calls and then return a self-reference. So that's basically all the properties of TACAI and how it looks like. And next we can jump into our evaluation. To evaluate it, we had seveal research questions. At first we wanted to know whether the performance of TACAI is still reasonable, because we have to perform abstract interpretations and we wanted to know if it's fast enough and feasible. Then we ask ourselves how the improvement in domains and using more precise domains influences the number of the 3 dress code statements in general. Then we also wanted to know how many times we have more precise receiver type information compared to Jimple, and we also wanted to know how using TACAI affects the precision of subsequent analyses, in particular car graph algorithms, which we tested here using a simple CHA algorithm, because you can see the effect there immediately. So, the first experiment, we wanted to know TACAI's performance implications, and when we consider the table on the left-hand side and there the runtime column for our 5 evaluation projects, we can see that Jimple is almost, for the projects, slower than even the most precise TACAI version with the level 2 domain. It's only slower for Java CC. Then we can also see that the overhead from computing TACAIL1 is almost negligible over computing TACAIL0. So we conclude that it's in general feasible to use TACAI, because it seems to be at least fast. But what's about the number of instructions and serial dress code statements? Now we know that it's quite fast, but as we can see, when we use a more precise domain, the instruction count is barely reduced for all the projects. So it's actually always less than 1% reduction in instruction counts. However, that's kind of expected, because otherwise it would indicate that there's a lot of that code within the project, and the interpretation finds paths to prune because they are never used. So it's actually good for the projects that we couldn't reduce the instruction count that much. But please be aware that all the projects are rather small, and bigger projects might yield other results. Next, our third research questions about the precision of TACAI's receiver type information compared to Jimple. What we did here is we looked for all invocation statements in the projects and tried to compare the results, the types, with those provided by Jimple. As you can see here in the table, there are many invocations and we could almost match all of them. The most failed ones in ProGuard are due to a bug in Jimple where it falsely eliminated JVM level exception handlers, which are obviously couldn't be eliminated. So there were some call size that we couldn't match, but all the others we could match. And we found that the type information for most of them are equal. So TACAI couldn't be more precise than Jimple there. But as we can see, TACAI was always at least as precise as Jimple, but in some cases was also better. So we have a little improvement. And additionally, which is not available in Jimple, but we immediately have available in TACAI, is nullness information, which we compute at more precise domains. So they are not computed with the base version of TACAI. And here we see that we can provide nullness informations for a lot of core sites, and there we don't have to consider null pointer exceptions. In our last experiment, experiment 3, we constructed a simple class hierarchy based call graph, and we wanted to figure out how TACAI improves over Jimple. And in general, we see that we have a great reduction in call graph edges compared to Jimple, even though we couldn't improve that many call sites. But when we could, we had obviously way more precise information. The biggest difference is for JAX, which is almost 60%. But between the different versions of TACAI itself, from level 0 to 2, we have a really minuscule reduction in call edges. So, to conclude, and to show you some future work, what we did in this work is that we extended OPAL with TACAI. It facilitates static analysis, and we don't have to implement them longer on Java Bytecode. Then we also have an intermediate representation that's configurable over abstract domains. We provide 3 preconfigured domains that are really available as TACAIL0 to L2, and we figured out that TACAI seems to be feasible. But our experiment shows that we still have to experiment with different domains and trade-offs. Also have to do more experiments. And we also want to check out whether we can encode other information within TACAI, e.g. String tracking information, by using abstract interpretations over strings in source code. Finally, let me summarize what we talked about. So at first, we figured out that what other intermediate representations do. Then we discussed how TACAIL looks like and what are the differences between the different configurations. We evaluated our intermediate representation, and in the end, I just wanted to thank you for listening, and you're also welcome to try out OPAL and to check out TACAI. You can find a tutorial on our website on how to use it and how to generate also the intermediate representations at different levels for a certain method only. So yeah, try it out. Thanks.
Now let me stop sharing and switch back to audio and video so that we can take questions. We already have 2 questions in our chat. The first is from Manas Thakur, at IIT Mandi, India. Does TACAI preserve bytecode indices, BCIs, from Java Bytecode?
So at first, I also want to apologize for the terrible video delay. Sorry, I don't know what happened there. And to answer the question, no, TACAI does not preserve the bytecode indices. And also, it's not possible to completely get the original bytecode out of the representation anymore once transformed.
Thank you. The next question comes from Tesla Zhang at Penn State University, and that one is, how does TACAIL2's alias analysis work? She supposes that alias analysis, or he supposes that alias analysis is difficult in general, and you seem to do a simple subset of it.
Yes, so the L2 alias analysis is, as I said in the talk, based on abstract interpretation. And we also do only a masked alias analysis. So we can also only have analysis alias information when we can be really sure that a variable must be an alias of another one.
Thank you. Then we have space and time for one more question, but I don't see one right now. So I assume that that means that we are done with the questions for today. Still, thank you very much for the great talk. Apologies again about the audio. I again assume that it was something on my end here. But very good work, and still no further questions. Then let us move on to the next talk.
Yeah, thank you.
Thank you.
Trace hope.